right, so good evening, everybody. Happy to welcome Robin. That's going to talk about one of my favorite topic. And finally, we made it, right? Somebody that can speak about federated machine learning, quite exciting topic. So, Robin, the floor is yours.
Thank you, Patrick, for the introduction. And I'm glad to hear that this is your favorite topic, as it's also my favorite topic. It's something that I work with, every day. That really drives me to realize in practice. The title of this presentation today, or I would say session, as let's do this interactive as well, is overcoming data silos with federated machine learning, realizing edge ML solutions. So first off, maybe 2 words about myself. So I did my PhD and studied in Karlsruhe. It's a city in the south of Germany where I'm still located at the Karlsruhe Institute of Technology. So I have a background, started very early in software development, web development, and then found my passion with optimization methods, where I really got excited in how you can design systems that really do things automatically that you couldn't do without it. And then there came this whole notion of machine learning that changed a lot for me, and that hooked me up, and I decided to specialize in that. And my PhD and my research, I focused on distributed machine learning. So whenever data or machine learning systems are distributed and I need to still realize them, this was something I conducted a lot of research together with the KIT, but also I had the pleasure to work with the MIT IBM lab in Boston on topics like that. And one thing that is a product of that is Prenode, actually. So I co-founded Prenode with my dear colleague Ronnie, who also conducted his PhD also at the KIT. And what drove the both of us was that we saw this technology, federated learning, and we fell in love with it, like you, Patrick. And we saw that this technology needs to be put into practice. It needs to be accessible for not only large companies like Google, not only large companies like IBM, but actually every company that wants to leverage the power of AI. And 2018, we founded Prenode out of the university as a spin-off, and we are now 11 people that work there, still located, as I said, in the south of Germany, in Karlsruhe, that has grown into a tech hub and one of the major areas in Germany for AI. And still growing, still working with a lot of companies and also universities. So this is a little bit about our background, so you can allocate me a little bit better. But let's dive right into the topic. And I think what most of you in the audience and me as well drives is when we think about machine learning, we of course are enthusiastic about this great technology that can do this and that and this and that. But at the end of the day, we need to somehow see how we can put this technology into a position where it actually makes an impact in practice. And for a lot of companies that want to use machine learning or AI, that means for them to combine machine learning or AI with a product or with a service, and then actually either have a better service that does something that this product or service wasn't able to do before, or that makes it more efficient, that makes it better in some sense, so the competition has a hard time. And there are a lot of studies on that, and one study we found is that companies are really profiting from having these machine learning or AI products in terms of ROI. But when we look into this machine learning or AI world, then what we see are examples like, for instance, Tesla, that all of you will know. And when we look at Tesla, what you see is a great system that cannot completely drive autonomous, but it can perform quite well and better than its competition. And why is that? That is because they have a huge load of data. They have like a lot of miles they drove already with this vehicle where they record this data that they can then use for machine learning training. And that is something that they have as a competitive advantage. The same thing as you go, for instance, with your Google Assistant that you might have in your home, or your Alexa from Amazon, that they have a huge sample of data that they can learn from to enhance their AI systems. And this is something that a lot of B2B industries, a lot of industry areas don't have in their products or services. If we take, for instance, the area of, or the industry of industrial manufacturing, that is very, very prominent in Germany, as you might know. There are a lot of major companies with that. And we say the same paradigm. I have my machine. I want to enhance it with my machine learning service. So I have this better machine. What you see is that they have a really hard time to gather enough data in order to realize their systems. And that not every machine is the same. And this is something that, Andrew Newton also says. You probably know him. He's ex-Google Brain, co-founder of Thing and AI leader of Baidu. And there's this article where he states that, okay, if you have like a system like Google has, you want to make a search engine better, you have 1 billion users and you create one AI model. But if you have like an industry, like the industrial manufacturing, you might have 10,000 manufacturing plants, but you don't have one AI, but actually 10,000 different AI models you need to train, as you have so many different situations locally. And you have to incorporate those into your training. And this is actually that one of the motivations for federated learning, or in a more broader sense, for decentralized machine learning. Because if you now look into the situation, what you experience is, as a machine manufacturer, for instance, what you can do in order to realize these systems, you can actually create, you have now 3 customers, and all these customers have their data that is in their local system. So let's take the industrial manufacturer, machine manufacturer, then the data of a machine at a customer of that company is stored on an industrial PC. It's stored on local devices, if you're lucky. And you might not be able to always access that data, especially data that is very interesting for you for your AI training. You might not be able to centralize that data. So what you could do, you could just create models automatically using automated machine learning on the industrial PC and create models there that you then put into practice. And that is something that in many, not only industrial, that can be done, that is also being done. But the problem is that you have not enough data. You might not be able to have enough data to create an AI model that is of sufficient performance. I mean, this is something that you might have already experienced in your practice. I know in finance there, you always have these huge restrictions on which data sets you can combine and which you're not able to combine due to legal reasons, for instance. By the way, if you have any notions, just interrupt me. So another option that you can do now is that you just overcome these barriers. You say, I will centralize all my data into these huge cloud data lakes. That is something that a lot of companies, of course, strive to do. You have these data ecosystems that even might emerge in different industries. So you just centralize all your data into one cloud. And then what you do is you create one AI model for all these different customers, and you can basically overcome that issue with that. As I said, that's sometimes simply not possible due to data sensitivity. In finance, you have in German law, you have this Trennungsprinzip and things like that, where you have to actually you're not able to combine data. You're not allowed to do that. Also, then in industrial area where we are like working a lot with customers, data volume plays a huge role. As you have maybe in a local industrial PC, or like you have in a local area, you have sensors that produces huge amounts of data per second, and this customer is in the middle of nowhere in the Swabian outer, I don't know where you have like very bad internet. So that is something that you have to also incorporate into your machine learning training, where the centralized aspect might not be able to succeed. And as I know that a lot of you are experts in data science, and I don't want to undermine that, is another option that you could solve that problem with, to generate synthetic data. So what you could do, you could actually use the local data and generate synthetic data based on that data. So one option would be to use GANs to generate the synthetic data to synthetically basically boost your training experience. But there are some downsides for that. And basically what you would do is you take your real data, you put this into a GAN, and you get like a GAN that is able to generate you very, very good new data sources. Now, the thing is, you have a huge risk here to introduce bias. You have a huge risk to introduce bias, and you have to have some kind of understanding of the real world data distribution. So what does that mean? So just imagine you have a customer where you apply that, and you don't have the full picture because there's still like it's a new customer, and you just record some data, and you just have a few data points, and they are extreme cases. And now your GAN produces data that doesn't resemble the reality at all. And if you have like an understanding of the distribution locally, you say, okay, that can't be here. That is complete nonsense. You can manually adjust that maybe, but this I just want to say to you, that's an option, but you have to actually put the work in here, because otherwise you will run into trouble and generate models that might have a good performance in your test bench, but it's actually very, very bad.
Robin, one question here for me.
Yeah, sure.
In your experience, did you already use synthetic data in a real life experience?
Yes, we had a case like that, but it's like where we generated image data, generated basically images that are you try to rotate objects on a picture and generate images based on that, but that helps you to.
They are not purely synthetic in this case. They are.
No, they're not.
Variations of existing data, right? Or
and there it worked quite well. But another case that we did, I don't know if you have time later on, but we benchmarked, like we did a benchmark of having GANs generate synthetic data compared to federated learning, compared to isolated training. So this is something, but this was an academic work. So I'm not a huge fan of data generation, synthetic data generation. But maybe there's.
As you mentioned, it can introduce bias because you don't know the data distribution. It might be biased, and then you just exaggerate the bias even more.
Absolutely. Right? This might be good for a POC. So if you have like a consulting case and you have a POC and you want to just, you just put a lot of effort into one data set, but in real life, when you actually, like my experience, my humble experience, if you put these systems to practice, you have to automate a lot of things. And when you automate things, the danger is, in my sense, often too high.
Okay, thanks.
You're welcome. Yeah, and I mean, another option is basically to change the paradigm. And this is something that federated learning is also based upon. And that is to use like this notion, as you all have heard, like neural networks, they are black box models. They are you're not able to understand them quite well, although there are explainability streams. I know that, but basically, what you can use this black box model as a means of information transport. So you use your model instead of the raw data to transfer and overcome this business problem that you cannot centralize the data with this technical characteristic of neural networks being black boxes. So
just one more question, Robin. I
yeah,
just
sure.
saw there was a Q&A here from Sebastian. How can synthetic data sets be tested? The normal train test for validate split approach does not seem to be applicable to synthetic data.
I mean, you can basically just, you have to, you actually, I saw that, like people generate synthetic data and they put the synthetic data also in the test set, but that's the first step. Don't do that. So just create a representative test set that you can test your models on. And but still, then, like my argument would be, if that happens, that you don't have this complete distribution, you never have a complete distribution, but almost representative distribution, you don't have that. How can your test set be good for that? I mean, that is an issue that you always have in machine learning. But with synthetic data, you're boosting the number, but are you really boosting the performance? I'm not saying that's never a good idea, but generally, like, be cautious about that.
Okay. I'm sorry for interrupting, but just...
No problem. Always. Yeah. So basically, you use these neural networks as a means of information transfer to store the information there. Now, maybe we can talk later, and I hope the question comes. Yeah, but can't you extract information about this neural network? There are methods for that, and if there's an interest in that, we can also talk about that later on as well, if you are interested in that. So just write in the Q&A if you're interested in that, and we can address that. But now we just have some methods that use that paradigm, and one method would be transfer learning. Transfer learning is basically using the notion of having a huge data set that you trained your model on, and then actually transferring it to a different type of machine learning case, or even the same type of machine learning case, but different data set. So just a different data distribution, and basically retrain it on that data set to gain a better performance on this maybe smaller data set. So you know a lot of models like GPT-3, for instance, but let's just look at one variant that we also see that machine manufacturers sometimes do. So the innovative ones, you see that they have and probably some companies in other industries as well, you have a test bench. So you have maybe a very, very good means of a data set that you think is very large that you can learn from, and you train a machine learning model on that data set. And then you take that model and you transfer this to this local IT system, and you basically just retrain it on this maybe smaller local data set, so that you gain a better performance here. I already said it, like there are a lot of pre-trained models that you, if you did image analysis, you probably used already, like Inception V3 or Exception. That is a viable option, and also to create your own standard models for certain cases, that might be an option, but it's the same principle, using a neural network as a means of information transport to boost your predictive performance. There are, of course, like GPT-3 models that are really powerful, that help you to kickstart your project. So that is something that, yeah, that is a viable option here. But what you don't have a learning from customer B to customer C. You just have your one-way street in that paradigm. Another thing that we did a lot of research on, that I just want to show you in a general manner, as to give you a glimpse about that. What you could do, you could train a model on one customer's data, then take that model to a second customer, retrain it, and then take the model back to the third customer and retrain it there again. So you would have one model in customer 3 that learned from these other 2 customers. That is something that is, yeah, there are a lot of problems that you need to overcome. One would be the sheer growing amount of combinations of ways of paths you could take through a network with more than 3, more than 4, more than 7, more than 10 participants. But there are ways of doing that. And there are ways of gaining really good results with that method, but you have to adjust a lot of training parameters to optimize that. So this is a very special case. But now, like Patrick, this is for you. Now we come to the federated learning part, and really generally how that works, as I'm sure that some of you might have just heard the term. And what I show you now is the vanilla, so the standard federated machine learning technique that is out there. And basically what you do is you train machine learning on neural networks on this local data source. You do this for every customer in your sense here. And then you centralize these model into a central, might be cloud environment. And what you do is you then fuse these different models together. One way would be, if you have a neural network, to basically extract the information from the neural networks as a matrix, and then do like an operation like an averaging over this matrix, or weighted averaging, or apply even fancier methods like a meta machine learning method that determines the optimal fusion of these different nets. And what you then have is one model that learned from all these different customers, and you resend it back to the different local environments. And you do the same thing again. You retrain this one model on every data set, and you centralize it again. So one cycle here would be one iteration. So I say one iteration, as we will see it later on in the hands-on demo, hands-on walkthrough. That would be one iteration. You also have locally, if you ever trained a deep learning model, you have epochs that you where you put the data through, and you have this adjustment of parameters. Just think of these iterations as a global epoch. So you over time, you will see later in the example, the learning decreases over time, and you have extracted the knowledge from all these distributed entities or distributed customers after some time. Yeah, so this is basically federated learning, but I'm not going to stop now, and I think there are a lot of paradigms that I just put out there, but we'll look into that in a demo in a second. Just what you might have already realized is that this is it might be a simple paradigm to grasp, but to realize IT systems that actually are capable of realizing something like that, of ensuring the data security of the communication, the stability and everything, that was actually something that we think, or we thought back then, that should be made easier. And this is, I don't want to be like advertising our solution, but I will use this tool for showing the hands-on federated learning in a second. We developed a solution here that's called MLX. And MLX is basically a suite that consists of two software components. One component that is installed in the local on a local device, maybe in the industrial machine, on the industrial PC, or in the finance area, might be a private cloud. It doesn't matter. It's Dockerized. And then you have a second component, is we call it central node, that basically does all this orchestration of models, that the management of all these different models that flow around in the system like that. And that also serves as a hub for a data scientist to create your pipelines, or load your pipelines from Azure or whatever into that system, to distribute them into these distributed systems. Yeah, Patrick?
Yeah, we just had a thought, right? Can you imagine that, for example, we could, because one of the biggest concerns with machine learning and AI is that we have to share our private data, right? Or people need your data or private data to train models, right? So can we imagine that some models, right, could be trained on one smartphone, and then somebody would just collect the models and make it like a global model, right? We can think of this for example, health insurance could be a model, because then you wouldn't have to share how many steps you take every day, or your heart your rhythm and things like that, right? We could imagine going to a kind of extremely distributed kind of federated machine learning model. Did you come across such ideas? Like
Absolutely.
Mhm.
Yeah. So I think this is the, especially in Europe. So in Germany, like the privacy laws are very, very high, for instance. But also the sensitivity for sharing data also amongst business partners is very, very high. So that becomes crucial and will become more crucial in the coming years. So if you see successful players that focus on privacy, is like if you know Apple, for instance. So Apple is using this federated learning technique in their iPhone quite heavily.
Yes.
And this is something where you have exactly that. And what we think, what our notion is, we want to basically be the infrastructure for vendors to use that into their products. And because for insurance, it's the same thing. I mean, if you have an app for that your customers can install and track their behavior, I mean, it's a one thing to basically discriminate them or like give them a different pricing. The other thing is to give them individualized services, or in banking, individualized private advice. That's exactly the thing. That's
because I believe that people would be okay as long as their data stay on their smartphone, right? But probably train a model. Well, the tricky part is that when you send the model back, it might be that the data could be kind of rebuilt, right? Or re-engineered back. I don't know, right? There was some research done on that, right? But there's a question, in fact, for Miguel, right? Miguel, you asked the question.
Just playing around with the chat screen. So yeah, I have one question, Robin, about this paradigm, federative learning paradigm. Would you consider like the resource needs and resource computation is one of the key challenges of this paradigm? Because I've seen the way that you have to train a model, and the customer then have this global model. There's a lot of interaction back and forth. So I am assuming that the computational resources and need and power is really expensive, or could be very expensive. So I'm not sure, based on your experience, if you consider this as a key challenge in order to implement this.
So having like local compute power, basically.
Yeah.
So
I mean, when you are planning to put together this infrastructure in order to be able to do this federative learning, I guess that could be a for a client, or could be potentially a huge expense.
So I have to answer a question and discriminate like some industries. So if you talk about consumer products, if we talk about the iPhone, if we enhance an application, the app with that, I don't worry about computational power, because these devices are they are really powerful. You don't have any issues with that. If we think about industrial machinery, there we have what we see is that edge computing, so deploying machine learning models on site, or having more power on site on edge devices, that's something where a lot of machine manufacturers invest heavily in. And it makes sense. If the machine costs $500,000, why would you hesitate putting an additional PC or industrial PC for 5,000 in that machine, or even if it's more expensive? This doesn't matter. If it enhances the service business, then it's a no-brainer. So that is what our experience is. Right now, it is a limitation. So If you want to do really heavy vision machine learning, like want to have some video analysis, things like that, you need to have some dedicated hardware. And this is something where we work with vendors to realize that. But for a sensor stream or something like that, I don't think that the IPC that you already have is not sufficient enough. So I don't think the problem is too critical industrial domain. And one thing that you also shouldn't underestimate is the private cloud paradigm. So IBM has this hybrid notion, right? The hybrid cloud concept, where you have private cloud and this public cloud. And if you have basically a private cloud, you can also have your elastic services. So I think, yeah, true. If you have very heavy machine learning service, but so far that was a worry of us, but it hasn't really be one in practical applications. But it's something that always someone asks,
yeah.
And we ask it ourselves. But no, like there are questions like, but then that and that, and then we do a POC, and then okay, that's actually not a problem for the case you want to solve. Have you a specific case where you say that's an issue here? Or an industry where you think that computational power is not sufficient?
Robin, I could maybe take this question, because I was thinking on a case I was actively working in the past, and when Patrick explained me about this federated machine learning, I thought, oh, this would be actually a real use case, and we should really go through it. And I pick up the phone, I call the federal office in Switzerland who collect what's the so-called suspicious activity report for the banking industry here in Switzerland. There is an office in Switzerland, and I asked my guys, look, you collect all these reports, and how can we could help with this to build up a model, and this model could go back to the banks, and everybody could take advantage, because you have the real data, because the bank, they are sending only a piece of this puzzle, and you have the real puzzle. Well, immediately the answer came very straight: no, we are not allowed to give you the data whatsoever, because this data is not ours. We use it only for reporting purposes. And then he told me, go to each bank and propose them that, because it is not a bad idea. But then comes again this chicken and egg dilemma. So because then I go to a bank, and the bank tells me, yeah, do you have a model to propose, or do you want to build the first model based on my data, and then you want to propose it to be recorrected with the model, with the data from another bank? And then how it is going to be, because already talking about models will reveal so much about my business, because you might say, okay, my model is built out of, I don't know, 100,000 records, and already the other bank will know, oh, I have 100,000 clients, and I don't even want to know that, and stuff like this. So how we can prevent to really make sure that this model doesn't reveal anything to the other, because there's always the chicken and egg. No, who is going to be the first one who provide the model?
Absolutely. So I totally agree. So when we so this is a question that this is a business problem, right? Exactly. As you can imagine, when we started our company, we thought a lot about, okay, how are we came from technology, we had this technology and wanted to find an application. We thought about, okay, where can we apply that, and what different types of situations do we have? And we saw that we have that one paradigm where that you described. You have independent collaborators, independent banks, for instance, that want to have a joint model, that are competitors to each other, right? And they want to somehow have an advantage to that in, I don't know, like a joint venture or things like that. And we discussed this idea with a lot of insurances. We also discussed it a lot in the finance industry. And the solution was to create a joint venture that owns the models. Yeah. And then we said that can't be. So that is too slow for us. But I'm sure that in the future, that so I say it's very hard. You have to be politically very, very strong to realize a system like that, and you have to have a lot of patience. So I think we're good. We're well connected. We don't have that. We're not patient because we're a young company. So what we said instead, let's address an integrator. So our game was to address vendors that have this integrated view and the power to actually just deploy things and to actually just say, this is a part of my software. Either you agree to the terms or you don't have it, and you don't have customers that compete with each other directly, and they just have the notion, either I use a model that is inferior or I have a way better model and then I save 20% of my efficiency. And that is something where the customer says, yeah, I rather take the money. That's my answer, but I know that this is a problem, and my prediction would be, my humble prediction, you have way more insights into that, would be that when the pressure will be too high, there would either be the notion to create shared data repositories to create services that are superior, or, and that is a better trade-off if you consider that, to create systems like federated learning systems that do the same thing, achieve the same thing, but have a lower barrier. But I think the pressure needs to increase before that happens on these vendors.
Yeah, no, absolutely. No, I follow you on your answer. Yes, absolutely. Yeah, fully agree. Okay.
Okay, so I would just move on as time progresses. So I have one case I brought with me today. And this might be something that could be applied in the insurance area, but basically what it is it's the prediction of aftercare needs of post-operative patients. So this is a data that we gathered. It's an open repository. It's the HAR data set, but this is something we can share and be completely transparent about. So I hope you understand we have public data here. So the case is that you have hospitals that gather data from the patients, and they have this on premise in a local industrial PC, and you have this need to better basically provide a prediction or a recommendation on how patients behave after the operation. So the data we have here is basically recordings of 30 individuals, and they are in this aftercare and they're performing daily activities, like around 10,000 instances. And what we want to do is we want to do a multi-class classification of that data. So in that case, it's a variable that detects, we'll see it in a second, the acceleration in 3 axes. So you can say, is this person standing, sitting, or lying, and walking upstairs, or walking downstairs. So that is the machine learning task that we want to do, and the data we have looks a little bit like that. So really rough image here. I hope that's okay in this context. So this is how this looks. This is the data, and you want to predict whether or not the person is sitting, standing, and with that data, the doctor can then analyze. Either you put another machine learning on top of that, or the doctor can then decide, maybe recommend the patient this or that. Now this is the data, and the system, how it looks like is like that. So you have your this is the demo case. You have your aftercare application, and this application then recommends you, and the doctor can use it to give you some insights on how you should behave to better your treatment. And you have your MLX software installed on the wearable directly in this case, and you have this central cloud instance, the central node that orchestrated that training. And as we saw earlier, you have our machine learning models that are developed locally on the wearables using this private sensor information. MLX then locally trains on the edge these different models and then centralizes those, fuses those, and you can do all the things with that. So this is basically the case, and we can now dive into the demo and see how it works, because I think that is more interesting. And I have to stop sharing for a second, so bear with me. What you will see now is the demo environment or the user interface environment that that a user, a data scientist that works on that case will see. So you log into the software and then you see this. And in this demo environment, we have a lot of different edge cases. You have a map here, and you have these different patients here as leaf 1, leaf 2, leaf 3. In this case, just the 3 of them to make it easier for that case. And what you see here, you can click on it, and what you basically see is you see a set of models that have been trained on that specific data set. And you can further evaluate those with some parameters, or you can deploy those and put them into practice to actually do something. You see the availability in the last 24 hours. You see CPU load that will go up later on when we start training actually. And yeah, how many API calls there were. So that's basically one local environment. If we go back to this overview, we can select other ones as well. So this is your command center where you control your decentralized machine learning. And I will just walk you through how you would do that. And machine learning always starts with data. And as a first step, you can just define certain data schemas that you want to use for your federated learning. So for the motion detection, I already created a data schema here. So this is a JSON format. Is it large enough? Can you see it well?
That's okay. Yeah.
I can just do that.
Oh yeah, that's better.
That's better, right? So you don't have so this is basically the data schema that we have here. This is represents one data point. So you have a certain set of features, 1 to 22, and these are basically readings from this variable device. This is one window of that you want to classify. So is this person in that window standing, sitting, or walking?
Yeah.
You have to capture date, and then the target would be which class this person was in.
Mm-hmm.
And this is the data schema. We also have in this environment other data schemas. So these are this demo environment. So we have an industrial case here as well. And second step would be to create a data split. So this is something that you still have to realize in federated learning. You have to somehow define a data split. And Jorge, I think you said this earlier. We're not allowed to see how many data instances there are locally, right? So how are you going to split your data and make sure that you're using the right training and testing split, or for 2 models the same test split, if you don't know first how many instances there are, and second, you don't know which ones are which ones, right? So this is something that was also one of the challenges that we saw back then, and a lot of federated machine learning approaches don't address this. This is a decentralized data tracking that you need to realize. And we do this with distributed hash tables that serve as a proxy to make this mapping. So it's specific, but maybe some of you are interested in that. So what I just can do here, I can select certain data sets here, and you can just say, okay, I want to do train test split. You can also create a validation split. This is disabled in the demo, but this is just something like you just do your slider here like that. I can create that. But later on, I will just use something that I created already, because this is a random thing, so we can compare results later on. I will use the demo split. So this is how this works. Now I have a data split, and now I want to actually go into the machine learning part. So for us, I mean, if you are a data scientist and you want to realize federated learning, you probably have a data set in the central environment that you did your POC on maybe. and you have a pipeline already in Azure ML or in your Google Colab notebook or even on your local machine, and you want to put this into this decentralized system. So what you do is you create like this demo test task. So you create like a task. You say this is a multi-class classification problem, as you want to predict that. And now you select your split that your schema, your demo detection, and you say I want to predict my target. And then you can just say, okay, I want to use Keras as a machine learning framework to realize that. You also have other options here, but let's stick with Keras. And then I prepared, as I always am anxious with live coding. I prepared this, so I don't have any typo that keeps us awake. And this is basically, sorry, this is the wrong, I incorporated the wrong one. We just paste our model definition here. So I just import all my necessary components I want, just as I had a notebook. And then I just add my layers. And this is just a convolutional neural network with certain layers. I think it's not as important to go through all of them because it's just a neural network. You can put in everything you want and you return just the model here. You can also upload one. You have to decrease the thing here. And then we go next. And now you can also go, and this is crucial. You have to, our tool is made by data scientists, so we want to have like a lot of options for metrics. You go into that and you can define some pre-processing steps with Python and have a lot of options here. We cannot go into detail to everything as time's running out. Do all this next, and then you have your task. And now I just have this task created, and let's just start one run. So federated learning, bam, start this test run. We take our motion detection demo task, and I just do 5 iterations as time is running out a bit, and then select an optimizer, accuracy, this motion demo split, and then we start this. And in the meanwhile, oh, sorry, I took the wrong data split. I think this is the right one. Yeah, so now this is the correct one because it didn't match to the data. So now this starts now. And what I want to show you really briefly is one that we conducted earlier that shows now how you can experiment with that federated learning. So this is one pre-trained run. And what you see here is basically a performance graph for the different leaves. So for the different participants, let's just take this one. What you can now do in the tool, you can basically select and deselect different metrics that you want to track here and that you want to experiment with. And you see now that on the y-axis, you have your different iterations. So local trainings, centralization, and local trainings is one iteration. And it's done, in this case, 30 times. And your performance on the y-axis that goes up and increases over time. And you also have your local epochs, right? And this is something where I think you see the advantage of federated learning, or like how it works pretty well. You have your loss. So you have local, you put your data through locally. So these are your epochs. And then you cannot see it that well. I will increase the, no, this even makes it worse. But now you have your local epoch and you end your first iteration. You send your model back and you get your average model. Then you start here in the local environment with your loss. So the loss decreases over time. And you see that over time, you have this flatlining and you see, okay, maybe my model is ready now, or maybe I'm overfitting here.
So when you send it back, your loss goes up again, right?
Your loss gets up again, but a brief period, and then it goes way down. So you have this notion, you go down here, it goes up here. And I have some slides where I can show it later on a little bit better. So really briefly, here you also have the same thing. Now we didn't do that many iterations, but just for you, to know,
So between each iteration, you send back the model, its average, and then send back
Absolutely.
again, right? Okay.
Absolutely.
Okay, interesting. Yeah.
So, but Robin, this is like when you have your Gauss distribution curve, and what you are doing through the iteration, what you are targeting is to flatten the distribution as much as possible. Is this the same approach here? What you are doing, or because what is the business target? What you are doing to say to figure out which is the most positioning that the patients are taking, or what should they take? So what are we trying to achieve or to demonstrate with this data approach?
So the business goal is to create a model that is more precise, and that is being better, is getting better over time. That's the business goal. And for this patient experience, okay, maybe the business experience is not that, or the impact is not that high, but if you consider you have a prediction, you increase the parameters of a machine and decrease the faults, or increase the quality, or decrease the bad parts that come out. Every percent you get better with this prediction, that translates directly into profit for our customers. And what I wanted to show you is with that dashboard is like, and this is one of the messages that I want to send you here, is with federated learning, you have to experiment. You have, when you apply machine learning just in a regular manner, you have to experiment, right? You have your projects where you try this and that and this and that. But with federated learning, it gets even, I wouldn't say more complicated, but it adds another layer of complexity. So I prepared one chart, and then I think we are over for that. This is what I mean. You have to have this experimentation. Over time, on the left chart, you see that the performance goes up for every iteration. But now as a data scientist, you also want to check, how is my loss behaving? Is this going into the right direction? And there might be some funny things that go on. But my notion is you have to check that, and you have to have a workbench that enables you to do that with ease, right? Because you have this closed environment locally. You cannot just put your model out and extract your log files. You have to have this bench where you actually get these insights.
But theoretically, in principle, if you look at the principle of federated learning, it's pretty simple, right? You have various machines or smartphones, whatever, that are training a model locally, right? And then you put everything together. This is going to be a better model because this is an average across multiple data sets, right? So, and then you distribute again. So in principle, conceptually, it's simple, but logistically it might be more complicated.
There are two complex. There are like 3 layers. So the first one is that you have this. You're building a decentralized or a distributed IT system.
Exactly.
And these are always very, very hard to realize. That is, I think, evident. The second thing is you need to, in that IT distributed system, you need to actually enable the data scientists to experiment and to have the tools that you are sure that your machine learning models, they get better and they are robust. Because you can screw up here like big time. You can screw up in machine learning in general, but now you have a black box approach where you have local entities that are closed for you. So you need to have these experimental measures as I showed you. These are plots, by the way, from our tool. That's why we have a high focus on creating these tools for the data scientists to experiment. And then the third thing, these are federated learning specific, and where you need an expert, or you need to be an expert, one or the other, in federated learning itself. Like there are a lot of challenges with federated learning itself. So how do you make the models secure that you don't have this extraction of raw data? So this is something that falls into the differential privacy or homomorphic encryption area, or you have to reduce communication costs. So these are federated learning specific issues that you have to address.
Yeah, because it's yeah, the concept is very attractive, right? But
Absolutely.
the implementation execution seems to be full of challenges.
Absolutely. But let me say, like, I have 1,000 slides, a thousand discussions and cases that I could talk about. So as the time runs out, I would really urge, like, all the participants, I think there are 20 or more people here. If you have any specific questions, just reach out to me. We can continue the discussion, but try it out. Really, like, we have so many customers and partners that where we see that this is a missing link technology. Like, either you do it with us or with other vendors or other open source frameworks that are out there. I would recommend making your life easy, but do it and really experiment with the technology, because it is really an impactful technology that will, I think, be very dominant in the market in the coming years in data sensitive industries. So thank you for your attention so far.
Thanks for the last remark. I like it because I tend to agree with you, right? But especially with the GDPR and all the challenges and the concerns about data privacy.
Yeah.
Right? That's for sure. That's the future. So anyway, thanks so much, Robin. Right?
You're welcome.
We spent an hour, right? The time flies.
Exactly.
We had a few questions. I think that was quite clear anyway, right? Happy to connect. I would encourage the the participants to connect with you, right? If they have any questions. Anyway, we will upload the video, the recording on our
Great.
on our website and on LinkedIn, so people can take a look at it, right? And again, thank you so much, Robin, for taking the time to talk to you, to us.
Thank you for having me.
Thank you, Robin. It was really extremely interesting. Yeah, and then especially that you make very clear these three elements, which are the success for the three factors, because this technology, people forget how still fragile it is, that we need to do this. And here we are talking one company or one legal entity, but if you think, oh, we are going to do 10 partners, 10 banks, this is still another layer of complexity, yes, of course.
Exactly.
Also very interesting. Yeah.
Have a nice evening, everybody. Thank you so much.
Okay, Robin, thank you very much. Bye-bye.
Bye.
Bye.
Bye-bye.